Okay, so let's get started. So this is our last day of lectures, basically. And if you update to the latest, so I've kind of reorganized things. So, and of course, I'll do a lot more in the next few days or before New Year. So if you see, I started adding links to the actual content because this was the original plan. And I think we went through most of it. We didn't do dimensionality reduction, but we did a bunch of most of the other things basically, and I'll learn a lot more. I didn't get to spend a lot of time on this, but I'll just warn you in the end of today's lecture how you could go to jail for following orders, examples, data scientists in prison. So, I have a couple of books you recommend you read. Because the problem with all of these predictive methods, especially with lots of data, is you can propagate status quo, right? I mean, that's all you're doing, right? So sometimes propagating status quo could be actually against the law of the land you're propagating the status quo. Yeah, so I just put all these links here. So these things will eventually get babbled into a Git book. Let's see if this link worked. So this is Thus Spoke Zarathustra. I don't know if you read Nietzsche's. So anyway, this is from Adam's last example. So we'll train our LSTM to speak Nietzsche's words. Kind of cool. Okay, so let's go here. I think the best way to get into RNNs is, so we kind of played with this. We did this already, right? We were playing with this little sequence example. We had a sequence of ABCDs, and did we do this? Okay. So basically, let's get our head in the game. So we're going to now build models that are going to take care of, let me think. Now, let's actually watch this video. It's only 12 minutes. It's the best 12 minutes. Because there's too many things you may need to know. Lots of concepts. Okay, let's watch this.
You obviously need a very good model trained on a lot of data to get this kind of result. And it's likely that the model that you're training in the assignment is just not trained with enough data to show this. But you can try. There are many other ways to learn embeddings that I won't cover. Now that we have models for individual words, how do we deal with the fact that text is actually a sequence of words? So far, your models have only looked at inputs that were a fixed size. Fixed size means you can always turn things into a vector and feed it to your neural network. When you have sequences of varying length, like speech or text, you can no longer do that. Now what?
You've already seen how a convolutional network uses shared parameters across space to extract patterns over an image. Now you're going to do the same thing, but over time instead of space. This is the idea behind recurrent neural networks. Imagine that you have a sequence of events. At each point in time, you want to make a decision about what's happened so far in the sequence. Imagine that you have a sequence of events. At each point in time, you want to make a decision about what's happened so far in the sequence. If your sequence is reasonably stationary, you can use the same classifier at each point in time. That simplifies things a lot already. But since this is a sequence, you also want to take into account the past, everything that happened before that point. One natural thing to do here is to use the state of the previous classifier as a summary of what happened before, recursively. Now, you would need a very deep neural network to remember far in the past. Imagine that this sequence could have hundreds, thousands of steps. It would basically mean to have a deep network with hundreds or thousands of layers. But instead, we're going to use tying again and have a single model responsible for summarizing the past and providing that information to your classifier. What you end up with is a network with a relatively simple repeating pattern. with part of your classifier connecting to the input at each time step, and another part called the recurrent connection connecting you to the past at each step. To compute the parameter updates of a recurrent network, we need to backpropagate derivatives through time, all the way to the beginning of the sequence, or in practice, more often, for as many steps as we can afford. All these derivatives are going to be applied to the same parameters. That's a lot of correlated updates all at once for the same weights. This is bad for stochastic gradient descent. Stochastic gradient descent prefers to have uncorrelated updates to its parameters for the stability of the training. This makes the math very unstable. Either the gradients grow exponentially and you end up with infinities, or they go down to zero very quickly and you end up not training anything.
So do you guys understand what he means by those
These problems
delta
are
W's?
The exploding and
Sorry, the delta W's that are going to, yeah, the delta W's are coming from each of those W's in your, what's called the unfolded recurrent neural network, because you treat each time step as a different layer. So when you do it like that, and because of parameter tying, right, the same W is everywhere. So then you run into this sort of problem. Because all the delta W's are contributing to the same W.
Vanishing gradient problems. And we're going to fix them, surprisingly, in very different ways. One using a very simple hack, and the other one with a very elegant but slightly complicated change to the model. The simple hack is called gradient clipping. In order to prevent the gradients from growing unbounded, you can compute their norm and shrink the step when the norm grows too big. It's hacky, but it's cheap and effective. The more difficult thing to fix is gradient vanishing. Vanishing gradients make your model only remember recent events and forget the more distant past, which means recurrent neural nets tend to not work well past a few time steps. This is where LSTMs come in. LSTM stands for long short-term memory. Now, conceptually, a recurrent neural network consists of a repetition of simple little units like this, which take as an input the past, a new input, and produces a new prediction and connects to the future. Now, what's in the middle of that is typically a simple set of layers, some weights and some nonlinearities, a typical neural network. With LSTMs, we're going to replace this little module with a strange little machine. It will look complicated, but it's still functionally a neural net. And you can drop it into your RNN and not worry about it. Everything else about the architecture remains the same, and it greatly reduces the vanishing gradient problem. So what does this little machine look like? Remember, we're doing this to help RNNs memorize things better. So let's forget about neural networks for just a moment. Imagine that you want a system to have memory. You need to do three things. First, you need to write the data into the memory. Then you need to be able to read it back. And then you also want to be able to erase it or forget. Here is one way to write this very same idea down as a diagram. You have a memory, which is maybe a matrix of values. You also have inputs coming into the memory, and a little instruction gate that tells whether you are going to write to that memory or not. You also have another gate that says whether you're going to be able to read from that memory or not. And then you have one final gate that says forget the data or write it back. You can also write out those gates as multiplying the inputs either by 0 when the gate is closed or by 1 when the gate is open. That's all fine, but what does it have to do with neural networks? Imagine that instead of having binary decisions at each gate, you had continuous decisions. For example, instead of yes-no gate at the input, you take the input and multiply it by a value that's between 0 and 1. If it's exactly 0, no input comes in. If it's exactly 1, you write it entirely to memory. Anything in between can be added partially to the memory. Now that becomes very interesting for us, because if that multiplicative factor is a continuous function that's also differentiable, that means we can take derivatives of it. And that also means we can backpropagate through it. That's exactly what an LSTM is.
That's the whole magic, right? Just take a simple memory model, you make it differentiable, and then you can learn because of backpropagation.
We take this simple model of memory, we replace everything with continuous functions, and make that the new little machine that's at the heart of a recurrent neural network. The gating values for each gate get controlled by a tiny logistic regression on the input parameters. Each of them has its own set of shared parameters. And there's an additional hyperbolic tangent sprinkled in here to keep the outputs between -1 and 1. It looks complicated, but once you write down the math, it's literally 5 lines of code, as you'll see in the assignment. And it's well behaved, continuous, and differentiable all the way, which means we can optimize those parameters very easily. So why do LSTMs work? Without going into too many details, all these little gates help the model keep its memory longer when it needs to, and ignore things when it should. As a result, the optimization is much easier, and the gradient vanishing vanishes. There's one more thing to discuss about LSTMs. It's regularization. You can always use L2, that works. Dropout works well on LSTMs as well. As long as you use it.
Do you guys remember what's L2 regularization? Of what? Yeah, so you're penalizing by the size of the weights, basically, right? So remember we did the L2 regularization for, we call it penalized ridge regression, right? All it did was there was a hyperparameter that controlled the size of the weights. So if the larger weights get a higher penalty, right? Same exact idea.
It on the input or on the output, not on the recurrent connections. Now you know.
Oh, and then you asked me what about dropout, right? What's the... So I started reading the few pages on dropout in the deep learning book. So dropout has the same theory as that behind what are those called? You know, when we did these ensembles with random forests, we take various subsets of the input and, you know, we drop various columns at random. Remember? Mm-hmm. And then we generated these batches based on randomly dropping out different features, basically, right? It's exactly the same justification for this dropout. And the way they sort of implement it is by masking, you know, so they have, so they'll grab a batch and then there will be some, you know, there was a probability of dropping out, right, at a particular layer. So they're using that probability, they just draw Booleans, zeros and ones, and apply them to these nodes. That way they mask what comes in and out. I mean, so so there is a direct connection to classical regularization, but I haven't read through, you know, the entire section yet. I'm not sure if there's any super deep theory beyond.
What can you do with an RNN? Lots of things. Imagine that you have a model that predicts the next step of your sequence, for example. You can use that to generate sequences. For example, text, either one word at a time or one character at a time. For that, you take your sequence at time t, you generate the predictions from your RNN, and then you sample from the predicted distribution, meaning you pick one element based on its probability, and feed that sample to the next step and go on. Do this repeatedly. Predict, sample, and you can generate a pretty good sequence of whatever your RNN models. There's a more sophisticated way to do this that gives better results, because just sampling the next prediction every time is very greedy. Instead of just sampling once at each step, you could imagine sampling multiple times. Here you pick O, but also A, for example. Then you have multiple sequences, often called hypotheses, that you could continue predicting from at every step. You can choose the best sequence out of those by computing the total probability over all the characters that you've generated so far. By looking at the total probability over multiple time steps at a time, you prevent the sampling from accidentally making one bad choice and being stuck with that one bad decision forever. For example, we could have just picked A by chance here and never explored the hypothesis that O could lead to a very sensible next word. Of course, if you do this naively, the number of sequences that you need to consider grows exponentially. There is a smarter way to do that, which is to do what's called a beam search. You only keep, say, the most likely few candidate sequences at every time step, and then simply prune the rest. In practice, this works very well for generating very good sequences from your model.
Well, I think there's like 3 more minutes, which is really good.
Let's look at some other fun use cases for sequence models. Remember, we've seen that one of the most entertaining aspects of deep models is that you can play Legos with them. You can mix them and attach them together, and then you can use backprop to optimize the whole thing directly end to end.
If you think about RNNs in general, they're a very general trainable model that maps variable length sequences to fixed length vectors. In fact, thanks to the sequence generation and beam search that we've just discussed, they can also be made to map fixed length vectors to sequences. Start from a vector, map it to the state of your RNN, then produce a prediction, then sample from it or use beam search, and feed them back into the RNN to get the next one. Now you have those 2 building blocks, and you can stitch them together. It gives you a new model that maps sequences of arbitrary length to other sequences of arbitrary length. And it's fully trainable. What can you do with this? Many things. Imagine that your input is a sequence of English words, and your output a sequence of French words. You've just built a machine translation system. All you need is some parallel text. Imagine that your input is sounds, and your output words. You've just built an end-to-end speech recognition system. Real systems based on variations on this design exist and are very competitive. In practice, they do require a lot of data and a lot of compute to work very well. We've also talked about convnets, which basically map images into vectors that represent the content of that image. So picture what would happen if you took a convnet and connected it to an RNN. You have an image going in and a sequence of things coming out. A sequence of words, maybe the caption for that image. To do that, you need training images and captions. There are a few data sets out there that you can use for that, most notably the COCO dataset. It has images and crowdsourced captions for them. You can train a model that uses a convnet to analyze the image and generate captions from them. And it works. You can get great captions, generated completely automatically, and it sometimes fails in very, very funny ways. What's really cool about those examples is that you don't have to know much about the problem that you're trying to solve. All you need is data, lots of data, and computers, lots of them. And off you go. You can build a machine learning system that often does much better than specialized, handcrafted approaches to the problem. So here we are. With those tools in your back pocket, you can now train models that can predict from images, text, sequences, or any kind of data for that matter. If you're curious, there's a ton more to learn in the field of deep learning. Things also change every day as new techniques get developed and people find new ways to use those models. Even with just what you've learned in this class, you have the tools to design and train real models on real data. So what are you going to try first?
Okay, so I think that's basically the last 12 minutes or so of Vincent's course, actually. So now you have a lot of concepts that you need to understand. So let's just start with this little example. So we this is just from a nice blog, actually. The links in the later on to it. So we're just going to generate a string, which is just the English alphabets, and then I'm going to just do a character index dictionary by enumerating it. So I can encode it into the reals, basically. I'm going to create my sequences of length 3 and create data x and data y as arrays. And I'm just looping through here and making my input to be A, B, C, and my output to be the following letter D. A, B, C, and D, B, C, D, and E, and so on. So I guess there will be 23 such pairs of inputs and outputs. That's all this is doing. And then, yeah, you can just look at what data X actually is. So this is just the encoding into the integers. And data Y is just, again, encoding. So this will be your C, and so on. So here we're going to train a network on the data. And we will simply use, this is simply calling all of this. So right now we won't use LSTM, we will just use sequential and dense from Keras. And that's what we're going to basically do here. This is just the same data generation that we saw above. Now what I'm going to do is reshape my, create my vector matrix X by reshaping this data X into len data X and seq length. Right, so seq length is 3, and the length of so the length of data X is okay. What is length of data X? Three, no. Yeah, 3. So yeah, so 3 and 26, right? So this gives me, so the output is going to be 26 because I want to predict all the 26 alphabets. And then 3 is going to be my number of time. Well, because it's because I'm pretending that I'm seeing, a sequence of length 3, right? So my time here is just 3 units. So that's so then you should think about what this means in the head, right? So we have input dimension will be these 3 nodes coming at us, and then my my hidden layer has 30 nodes, right? Because it's a dense all-to-all connected. So this is just a feed-forward neural net. That's what we're doing here from last time. And then, yeah, we are using the normal kernel initializer to initialize the weights, and then using the rectified linear unit as our activation function of the stuff that comes out of this 30 units. And then the next layer we're adding is, so it has the dimension 26 because that's the 26 categories we want to predict, and then we activate that with softmax, right? So we get these probabilities. So this is all as before. Oh, by the way, I added a couple more videos from Vincent's thing for categorical cross entropy. It's like a 45-second video, and then also something that quickly explains Atom. So you can watch it in one of the earlier notebooks now. Okay, so now we simply run this and fit the model and get the accuracy. And in here we're simply reporting the predictions. So what we notice is if we use a deep feed-forward neural net after some fitting, let's see how our predictions look. There we go. So W, X, Y, and Z, V, W, X is, yeah, I mean, it's not that great, right? So we have only 61% accuracy. Okay. So, so what's really bad here is we're not exploiting the sequential nature of the data, right? We just had these 3 things coming in, right? 3 nodes for the input, and then we have these 30 things. And so all these 23 examples are being fed in. And so what we would really like is something that takes advantage of the fact that this is a sort of a stream, a sequential stream. And that's sort of our next main goal here. Okay, so this is essentially the idea of 1D convolution Vincent was talking about. Okay, so here's the basic idea. We have some time index, or order index, and then that's my input. it goes through some cell, which could be a whole architecture in here. And then we simply roll the information back to itself, and then we get some output HT. And of course, we want to have a representation that's conducive to our optimization routine, so we unfold it like this. So if this loop goes, say, k times, then we unfold it k times here. So now we just have one directed acyclic graph that we can use for stochastic gradient descent. That's finite. Okay. So that's the idea. So Karpathy is this guy at Stanford, I believe. So I recommend his videos if you want a much more detailed lowdown on a lot of deep learning stuff. So his videos from Stanford are on YouTube. They're very, very good. So here is my LSTM, long short-term memory thing. So this is what's inside the cell. This is the LSTM cell. And this notation, yeah, it's not too bad to get used to. So basically, XT comes in here, and then you know, some form of the past enters here. And then what we do is, so every time things go through a sigma, you know, which is our activation, we're having dot products. So there will be some matrix W that's hitting XT before it gets sucked in through this node by a sigma, right? So those are all implicit here. So there's other nodes sitting here, right? Yeah, in Vincent's video, he showed you a whole bunch of W's when he explained the LSTM cell, right? So those W's are implicitly here. Here is another sigma, and then there is this hyperbolic tangent, which again takes values in the reals and remaps it to -1, 1. And then there's again another sigma. So anyway, they've come up with this functional form because it seems to work, and then you feed it back through here. So all of this is, you know, in Keras, when we call the LSTM add layer, it does all of this for you because this is a fixed architecture. You know, if you want to change this, of course, you can go into TensorFlow and roll your own. We'll come back to this one later. This is a more recent one called gated recurrent unit, where it has a lot less complexity. So instead of having a LSTM as an input, output, and a forget unit, and a hidden unit, here we only have you know, two versions. The output is directly coming from some convex combination of ZT. So it works for some models. So we will see pointers to this toward the end. And this is, again, just a recap of Vincent's video. So we have to unfold it to be able to do gradient descent. So here the W's and V's are all explicit. These are the weight vectors. And notational nightmare here. So H, what was H before, is actually O for output now. And S is the state. Okay, so this idea is basically back propagation through time, and then you have all these hacks to keep the gradient from exploding or imploding into zero. Okay, these are some other asides from Adam. So there are hierarchical variants of RNNs, and there is bidirectional versions of RNNs. So in the bidirectional version, you also get information from the future. Okay. It's a bad way to think about it in terms of time, but it's not that complicated. Say even in a translation problem, you have a full sentence. A full sentence becomes another full sentence, right? So, which means, you know, not only do you want to know the previous word, you need to know the word to the right of that word, right? So when you have those kinds of architectures, then it makes sense to have a bidirectional RNN. And so these are well defined, and you're not really cheating or anything. Okay, so yeah, so this is all mainly from the Google Brain team. Okay, so let's yeah, I really recommend Chris Ola's full post. I think that's this one, because you really need to walk through this on your own and understand that. So this is essentially a massive high-level compression of what's really going on. So you want to really digest this slowly, okay? So every step is explained here in detail. What is the missing W's, where they're coming from, and all of this. So let's okay, so obviously, do these things work? They actually work incredibly well, and they are pretty much the same thing that's being used in the US and China and India and everywhere, and Europe. What is different about Baidu and Google and Microsoft and Apple is their real treasure is the data, right? So this is the big war. So the biggest problems in cybersecurity is like stealing data that is being used to build these models. Because if you know the data, you know you can definitely fool the model. I mean, you can do crazy things. So anyway, this is Alibaba, another big company. Their model is actually all about turning data into their treasure, right? So they give all these free software to various companies that can join them, and in exchange, the companies have to share their data. Basically, give the data to Alibaba and whatever. So it's a good model. It's kind of the new gold. So let's start coding the LSTM variant in now. So we'll play with the same example, with the same sequence. The only difference now is here, you see. So I've added the LSTM layer. Okay, this is all Keras magic, so everything sort of explained in the blog in detail is already done for you in TensorFlow under the hood. So the main point here is we have the input shape. If you pay attention, you have two things here. You have x dot shape of 1 and x dot shape of 2. So what is this? This is coming from the second and third dimension of x, right? What did we do to x? We took our data x that we generated, and then we reshaped it by the length of data x, which is the number of samples, right? So that's just 23 in this case. And then the time steps, which is the sequence length, which is 3. Right? And then the feature space is just one dimension, right? Because there's just one number encoding the character. Okay. So so what we are pumping in here into the input shape of the LSTM layer with 32 nodes is these things, these sequence length and the feature space one. Besides that, everything else is the same. We still have a softmax activation, and phi dot shape of 1 will still give us our 26 alphabets. Okay, and yeah, do all these basic things, converting, because we cannot treat these as integers 0 to 26. We have to turn them into categorical variables and stuff like that. Everything else is the same. We just can run this and see how well you predict. It doesn't take very long, actually, so you can run it if you want. So what we should see is that it's significantly better. Okay, so the accuracy is nearly 100%, and so using this sequential, structural information helps a lot because there's, it's just C is to the right of B in more than one place, for example. Okay, so
could you explain parameters one more time on these the X shape of 1 and 2 and what does it actually expect there? These parameters?
Well, okay, remember if you compare with your so when you added the pure dense layer, what did you do? You just specified the number of nodes, right? And then the input dimension, which is typically 1D, right? Because you'd say, like, if you look at this, for example, it was 3, right? What is the data dimension that's coming in? And we had, what did we do here? Here.
Yeah, X shape of 1.
Yeah.
That was 3. So the dimension was
exactly.
3.
So we basically have, so you can imagine you have three circles and 30 circles, and it's all for a network. So those 3 circles are the sequences that are coming in, right? So now we have 2 dimensions there, right? So you have the 3,
yes.
But you also have, so you have to specify 3 for time now, and then the feature is 1, but it unrolls it, right? So it'll have like 3 copies. I mean, it's a different architecture now. It's LSTM architecture, not a feed forward.
So the first parameter is basically the length of the sequence. The second parameter is how big do you read.
Yeah, it's the feature dimension. So I could have like, okay, so for example, this is just syntactic backmapping, but I'm pretty sure we can have 3 words, or say 5 words. So we can look at batches of 5 words over sets of 3, contiguous sets of 3, for example. In that case, your feature dimension will be, okay, 5 characters, so 5 words. So if I have 5 characters, and then, in sets of 3, then I'll have a 3, 5, right? So 3, 1. It's just how you, in this case, we're just using 1 character for the feature.
And then the reshape you did, what were the parameters of that?
The what? The reshape?
You did a x.reshape. I think, are you at the wrong code now? Or?
No, yeah, now you're looking at the other one.
Yeah, so this other one I'm wondering about.
Yeah. Okay.
So there you, so keep on going.
Yeah.
There, right? NumPy does reshape data x, and you give it the length of x, the sequence length, and 1. What was the 1?
1 is the dimension of the feature, which is the 1 character.
Okay.
So it will be
like, it could have been a sequence of vectors then, and then you would have the 1 would have been the size of the vector.
Yeah.
Okay.
But then we have to change all of this.
Yeah. Okay.
So okay, so what is the moral of the story here? This is significantly better, right? So then, let's see. I want you guys to do something before. Right. So what would be good is to get your hands dirty. Please do this little exercise. So what we're going to do is try to use W for some kind of erroneous or corrupted data, because we can train this LSTM and then feed it some kind of corrupted data and see how well it does, right? Because remember, we're just training on just 23 examples, and we want to know how robust this is to errors, right? So this is kind of your exercise. So you can copy paste this cell into another cell just down below, and then try to see what happens when you feed in some erroneous data to it. See what the prediction will do. Okay, so yeah, I should have hidden this. Don't look at the solution. I mean, this is good for you, right? So you'll just a little bit more syntactic help. Play with it, and then we can have Fika in a few minutes.
Just pay the dates for those. Yeah, generate.
Yeah, but I mean, this the letter comes pretty busy one.